Alright, chemistry. We're back at it. We're also back to labs that look a little wacky compared to how they should be printed. Starting this one out with a lab, and then I have 3 sections queued up for notes here. I think I will get through all 3. Y'all may be a little ahead compared to where we end up getting in class. That's not a big deal. You'll have, again, you'll have access to these notes like at all times. Please keep checking my CBA daily. Hopefully y'all saw that there was a quiz Wednesday, which might be when you're watching this, or watching part of this, but anyway. I'm going to start here on lab page 21, which kind of spills over on lab page 22. It shouldn't spill over, but I don't know, it's something about how Google Docs reformats things when you kind of try to download them. Oh good, my pen is working. So intermolecular forces is a lab that we're doing Thursday in class. Yeah. And it's about intermolecular forces, which are the forces that keep molecules close to each other, right? Intermolecular forces, if they are strong, so like solids have very strong intermolecular forces because they want to be together. Liquid intermolecular forces are a little weaker, and gas intermolecular forces are very weak. All right, gases have no reason to be together. That's why you can pass through them. You can push them out of the way very easily because they are not held together very strongly. I don't know if that's a word. Anyway, the deal here, and if you want to do this and you have what you need to do it, you totally can. You just need a penny. I guess like technically 2 pennies, so you get, or 4 pennies theoretically, but a penny or 2. And you just need like a little eyedropper. Like if you have a relatively clean eyedropper, you can do this. Disclaimer, you may ruin an eyedropper by doing this with vegetable oil, alright? So I wouldn't necessarily recommend doing that. But the one with water is very easy. You take an eyedropper and you... but anyway, you can see the procedure is fairly straightforward. You take a penny, dry it off, right? Give it a good rinse, but dry it off. And then you'll put the penny down on a paper towel on the table because eventually things are going to spill over the sides of the penny. But what you will do is very carefully take the eyedropper. In class we had like dropper bottles, but take an eyedropper and just drop by drop, individual drops, drop water onto the penny until it no longer holds water over it. What you should notice is that over time, if this is the surface of the penny, the water will build up and up, obviously, and eventually it may start to spill over the edge, just barely, but it will still continue to allow you to pour water on it. And the reason for that, we call it like surface tension, or maybe you've heard the term surface tension before. Surface tension for water is the reason that it takes some effort to go into water, right? It's why if you're like jump off the pool and you belly flop, that's why it hurts, right? The water is there and you are displacing it, you're pushing it out of the way. But water tends to want to stick together. That's why water kind of gathers in puddles. And by doing it drop by drop, and if you're very careful about it, you can actually get quite a few drops on there, right? I did this 4 times, and when I did it, I got 62 drops the first time. I got 50 drops the second time. I got 64 drops the third time. And I got 60 drops the 4th time. I think the second... Oh, what happened the second time when I did it? There was a really huge drop that came out, and I had very bad control over it, so I did a better job later. That is an average of... That makes that 56... 59. The average there was 59. Sorry, I'm trying to do that in my head. Now the second time, right, completely dried off the penny again. And then I did it with vegetable oil. And with vegetable oil, I was far less successful. Now, the boxes ended up here, and the question, I don't know why. I'm just going to continue down here. Vegetable oil, I was much less successful. I only got 17, 15, 15, and 13, right? And that was an average of 15. And it should kind of make sense, right? Like, vegetable oil is runnier naturally. It also doesn't kind of like stick to itself, right? If that makes sense. Oil and water have different properties, obviously, but oil does not have the intermolecular forces that water does, which we will talk about right here. So what substance has stronger IMFs? And give proof from your data. Right. Oh, pen's upside down. Here we go. So for question number 1, water, it held more drops. Oh, went way too far. On the penny. So it held more drops. I was able to get more water on the face of that penny than I was oil, because the water stuck to itself. It wanted to cling and hold on. It was literally like spilling out over the edge and still wasn't spilling out over. What IMF is present in water? Right? Well, water is H2O, and where there's hydrogen, there is hydrogen bonding. Now again, hopefully remember from the last video, hydrogen bonding is not truly bonding. It's a really strong IMF. They thought it might be bonding, but it's not. It's just not an IMF. Finally, number 3, what reasons might we have like invalid data, and how would that affect the results? Right. Well, for number 3. What about the drop size? How big the drops are? I said for that second trial when I only got 50 on the penny, there was like a random really big drop that came out. If the drop size is not consistent, then 50 on one trial might be the same as 70 on another trial, right? So the drop size could affect literally how many it was. A clean surface for the penny might also affect it, because you get these inconsistencies, like the actual surface itself. If it was nice and clean, it should be a fairly flat surface. Even though there's a little engraving, it should be a fairly flat surface. If there's random dirt and stuff on it, right, that's going to change the surface. It's going to affect how many drops can actually land on the penny. Something that came up was like heads or tails. You might have heard like a superstition about coin flips, is that tails never fails, and people claim that their reasoning for it is that the face on the head of a penny, or on any coin for that matter, has more weight to it than the tail side. So their argument is that because as it is flipping through the air, it really wants to land head side down, because there's more weight on that side, because it's like weighted, right? It's like a weighted die. It's weighted towards that side. So does that actually hold true? Now, experimentally, I don't know that has had very much influence on things, but it kind of tracks. There's a different it's a different surface, right? Whether you have the head side or the tail side. But yeah, so that was just a quick little lab. And again, if you have like an eye drop, you can try. I feel like the high score, the most number of drops of water that people have gotten onto it, I want to say it's up in the 80s. Now, I wasn't there to like account for it. I wasn't there to count it myself, so I don't know that was super possible. But it's definitely more than you would expect it to be. Like, it's more than I expected it to be when I first did this. I was like, there's no way. No, turns out it was about right. Alright. So we ended our little thing with IMFs. The next section is page 85. And it's this section called Kinetics. Right, now, Kinetics is its own little mini branch of chemistry, and you should get an idea, like a little idea, about what kinetics implies. It should be like dealing with motion, right? Because kinetic energy is the energy of motion. Specifically, this is the branch of chemistry that deals with the speed of chemical reactions. Like, how fast do chemical reactions happen? Can we make them happen faster? Can we slow them down? Do they act differently if we do them faster or slower? And how can we make them go faster or slower? So, Kinetics deals with the speed of chemical reactions. Chemical reactions happen, like, they physically happen, or I guess they chemically happen, technically. But it's because of a physical reason. Particles collide with each other. Like, they literally just run into each other and they hit each other. Now, there's an asterisk, right? As with most things, we have to qualify this. It's not just that they hit each other. The speed of a reaction, so how fast a reaction happens, depends on the number of collisions and the fraction of those collisions that are what we call effective. Right? Some collisions are effective, some collisions are ineffective. If you watch a football game, which, by the way, boys football, hey, we won a few games. Let's go. Nice job. But you watch a football game, right? There are many collisions in a football game, right? Not all of them are effective. If you want to tackle someone, there are form tackles that you might want to do in order to get someone down. They're like big hit tackles if you wanna force a turnover, but not all collisions are effective there. Similarly, not all collisions are effective here. If two particles are supposed to hit like this, and they run into each other like this, that's not an effective collision. Even though they hit each other, it doesn't count, basically. So in order for it to count as effective, particles need to have enough energy. They need to be moving fast enough. They can't just like, maybe. They typically are moving very fast. And they have to be oriented appropriately. Which really just means they have to be facing the right way. Again, if they're supposed to collide like this to create a new compound, but they collide like this, then it wasn't effective. So they have to be moving fast enough, they have to have enough energy, and they have to be oriented appropriately. We have to turn them the correct way so that they actually hit each other. You try to backpedal and tackle somebody that way, you might be going fast enough, but you'll probably miss, or you might glance off of them. Right. So anything that you can do to increase the number of collisions is going to make the reaction go faster, or do what we say, what we will call increasing the rate of reaction. Right. Now, there are things that you can do to change the reaction rate. One of them has to do, and there are 6 of them are listed here. Right. Temperature is the easiest one. Increase in temperature increases the energy or the speed of particles, which increases the number of wait, why do we have of collisions there? Oh, this is just going to increase the total number of collisions. Just by sheer numbers, you're going to increase the reaction rate because you're just making more collisions. If you make more collisions, just by percentage, you're going to end up with more effective collisions. So temperature isn't a good way to increase like how they're facing, but it's a good way to increase just sheer number of collisions. The surface area. So think about like a sugar cube dissolving in a cup of coffee, or like a spoonful of sugar dissolving in a cup of coffee. Which one's going to dissolve faster? It's going to be the spoonful because there's more surface area. So as you spread out the surface area, the number of particles that collide increases, and because there are more particles colliding, you end up with more reactions happening. Right? Catalyst. Special. Catalyst lowers the activation energy by providing an alternate reaction pathway which makes the hill easier to climb, which makes the reaction rate increase. This actually makes it so that they don't have to be moving as fast. Basically, a catalyst, like literally what it does is it's a guide. So it tells them, hey, just go this way. It'll be easier. It'll make your life easier. So it actually allows them to have less energy, but still collide effectively. Right. Concentration of reactants. Right. A little asterisk next to 2. Surface area applies to solids. Concentration applies to solutions, things that are dissolved. Right. The concentration of reactants, which is the number of particles in a certain volume or in a certain space. If you increase concentration, you increase the number of collisions. Concentration is like the strength of a solution. If I go back to like the Kool-Aid or the lemonade mixture, if you put more instant lemonade in, you increase the concentration. Increase in concentration. Also, if you remember like the lunch line pre-pandemic time, if you try to jam a ton of people in there, it's a real small space. It's a high concentration of people. The more stuff, the more particles, right, that you put into a space, the more likely those particles are to hit each other. In which case, more reactions because more collisions. Now, the nature of reactants. This is a weird one, number 5. What kind of bonding there is can actually affect how fast something happens. In solution, what we find is that ionic compounds tend to react more quickly than covalent ones. And the reason for that is when ionic compounds go into water, they actually dissolve into more pieces. More pieces means more collisions. And then the last one here, finally, is pressure. That's supposed to be a star. There we go. Pressure affects gases. So increasing the pressure on a system that contains gases will end up increasing the frequency of collisions. Again, think about what we said about pressure. If you're increasing pressure, that means you're squeezing it into a smaller space. It's similar to concentration. If the gas is in a smaller space, it's going to hit more often. That means more collisions. All right? Now, the next page is going to get into something else. I'm going to pick and choose what I do here, so bear with me as I go through it. I'm picking and choosing mostly because without the regents as a handcuff, I can do what I want to do only, and then that leaves me a little time after we finish these notes to kind of look at some other chemistry things. So just, like I said, bear with me as I cherry pick here. The bottom of this page is good. We're talking about chemical reactions and how fast they go. We also want to talk about which way they go. We've always read chemical reactions from left to right. Turns out some of them you can undo. Right? I can reverse a reaction. So chemical reactions are actually frequently reversible, which means they can go forward and backward. And we talked about this with thermochemistry. We talked about exothermic and endothermic reactions just being opposites of each other. So you can write a reversible reaction two ways. You can have a split arrow, which is something that looks like this, or a double-sided arrow, which is exactly what you would expect. It's an arrow with two sides on it. When we talk about reversible reactions, there is a special moment that happens, or a special phenomenon that happens. So as time goes on, both the forward and the reverse reactions will be the rates. The rates will be equal. So how fast it's going forward and how fast it's going backward, eventually those two speeds will equal out. Right? At this point, the concentration, which is to say how much of the reactants you have and how much of the products you have, they will no longer change. Or they stay constant. So at some point, if you just leave a reversible reaction like in a closed thing, like you take it and you put it in a jar and you put the top on a jar, it will do one thing and then it will go backwards, and then it will do forwards and then it'll go backwards. And eventually forwards and backwards will happen at the same speed, at which point the amount of reactants and the amount of products that you have stays the same. It stays constant. When we do this, it's said to be in a state of, fancy word, which you've heard before. We say that it's in equilibrium, right? It's already starred for you. We have starred it for you. I'm going to star this before I get to it. But equilibrium can exist within both physical or chemical systems. It's an interesting kind of weird thing, right? But equilibrium means that the opposing rates are equal. It means it's going as fast forwards as it is backwards. It doesn't necessarily mean that you have the same amount of reactants as you do the amount of products. Those two amounts don't have to be the same. They just have to stop changing. When I say this can happen chemically, it means that a chemical reaction can be doing and undoing and doing and undoing at the same time. We talk about physical, it means that if actually this is like this is the premise behind a terrarium. If you take a little jar and you put moss and leaves and rocks and stuff in it, and you mist some water in there and you seal it up really, really good. You seal it up completely, right? You put actual like liquid water in there. There's also water vapor in the air. And what will happen is you will make a little mini ecosystem inside your terrarium where it will occasionally some of the water that's on like leaves and moss and stuff will evaporate into the air, and it will also rain back down, right? That's evaporation and condensation. Or yeah, evaporation and condensation. So you'll have a little water cycle happening where those changes are happening at the same time, at the same rate. So you'll always have the same amount of liquid water and water vapor in there. They just change back and forth, right? So physical equilibrium. Now, phase changes are examples of physical changes. What? Why is my... Hello? My pad is being a little weird. There we go. These are examples of physical changes. If you can get them both to happen back and forth, then they can be physical equilibrium, right? Now, I'm going to mention a word here that will come up again when I talk about solutions in, I don't know, 10 minutes or so here. But a saturated solution. Saturated means it's completely filled with what it has, but it's an example of physical equilibrium, and I'll talk more about physical equilibrium in the next section when we talk about solutions. All right. Now, this next bit, right? There's a lot happening here. I'm gonna kind of, it's gonna feel like I'm rushing through this, but the big deal, the big like concept that you need to understand here is what it means to like which way the shift is, right? And you'll notice the fourth and fifth bullet point, kind of like center of the screen here, talks about a forward shift or a reverse shift. All right. Now, this science guy over, which way am I pointing? That way, over there. LeChatelier. Looks like chandelier. I know it looks like chandelier. It's LeChatelier. He was French. I'm assuming it's a he. I'm assuming it's French. I hope. Anyway, so LeChatelier's principle is a principle that says if you have a system that's at equilibrium, if it's normal, so if it's regular, if it's just hanging out, it's going just as fast forwards as it is backwards, and you subject it to stress, right? And it uses this word stress in this context. Stress just means change. So if you introduce this system that's at equilibrium to some kind of change, then what the system will do is it will shift. It will change back in order to try to get back to equilibrium. And the example that we use is that if a room, now not the chemistry room, because when the chemistry room gets cold, it just stays cold, but when a typical room gets colder, right, the furnace in the house turns on to try to heat things back up to a normal temperature. Alternatively, if a room gets too hot, the air conditioning turns on to try to cool it down to a normal temperature, to our equilibrium temperature, right? Our bodies go through this. They follow this principle, right? If your body gets too hot, then you sweat. And the sweat is a process of an equilibrium. The stress is that you are hot. The shift, the change that you make in response is that you sweat. Now, the reason you sweat is because by sweating, you put water on your skin. Water absorbs heat from your skin and it evaporates. It takes the heat away from you, right? So the purpose of sweat is to naturally go away. That's a shift, right? Alternatively, if your body gets cold, your muscles shiver. The reason they shiver is to get your body to move. By making your body move, it increases your temperature to get warmer, to get closer back to your equilibrium, right? So there are different examples of stresses that we can do. We can change concentration. We can change the amount of stuff, so I can add more stuff into a system, or I can take stuff away from the system. I could change the temperature, or I could change the volume. So I could squeeze the system into a smaller space, or I could put the system into a bigger space. But these are all stresses. These are all changes that I can make to a system. When a reaction responds to a stress, one of two things will happen. Either the forwards or reverse reaction will temporarily take over. It will go faster than the other. So instead of being equal both ways, one of them will get shorter and the other one will get bigger, or vice versa, right? If you have a forwards shift, that means it will shift to the right. If you have a reverse shift, it will shift to the left. All right. Now, the example that I have here, and I tend to use like a seesaw example, right? So if I have this example here, where it's A and B, let's say A and B are on this side, and C is on the other side. And let's say everything is balanced, everything's in equilibrium. Okay, that's great. All right, if additional A is added to the system, so I'm putting more stuff over here, so whoop, that's what happens to my scales. If you're like the Justice, right? Justice is blind, but she holds a pair of scales that are supposed to represent balance. But a triple beam balance works like this. So if I put a bunch more stuff over here, whoop, that's not balanced anymore. We are no longer at equilibrium. I need to fix this. The way that I need to fix this is I need to go this way. I need to make more stuff over here. So I need to force the reaction to go this way. Now, for me, this is to my left. It might be to your right. It's hard to tell. I don't know what happens to the video when I watch it. But I need to shift the opposite way. So if I add something to one side, I need to go away from that side. My shift has to be away from that side. So I'll shift this way. To me, it's a shift to the left, right? If you look at the system how it is here, right? If I add to the left side, I need to go away from the left, so that would be a shift to the right. So the stress would be adding a bunch of A to the reaction. That means I'm adding stuff to the left side of my reaction. If I want to balance that out, I need to force the reaction to go to the right, because I need to balance out my scales, right? That's a concentration example. Gases are tricky. If you know that everything is a gas, right? Increasing pressure, which was another one of the stresses that I mentioned, but increasing pressure will always favor a shift towards the side that has the lowest number of moles. Lowest number of moles of gas. Remember that moles are just the coefficient. All right, so coefficient on the left side here is 2. The coefficient on the right, there's 1 here, there's 3 here, so there's 4 moles on the right. If you increase the pressure on this system, it says that it will cause a shift to the left, because there are 2 moles of gas on the left and 4 moles on the right. And what that means is that I have 2 moles on the left side, so that's, consider it 2 on the left, and 4 on the right. Well, 2 is less than 4, and if I'm in a smaller space, I want less stuff. So I want fewer moles. I want 2 moles instead of 4. All right. Let's start this last point. Adding a catalyst does not create a shift. It just makes everything faster. It makes everything faster equally. Right. The quick version, if you add something, will shift away. Oh, that's not how you spell away. My goodness. If you add to a side, it will shift away from that side. So add starts with an A, away starts with an A. If you take from a side, it will shift towards that side. Again, take and towards, they start with the same letter. All right. Don't worry too much about these 2 blanks. I'm not fussed over that. The short version is, if you're given a reaction and you add something to the left, it will shift away from the left, or it will shift towards the right. If you take something away from the left, it will shift back to the left. So adding is away from that side, taking away is towards that side. Alliteration, right? There are some practice questions down here, which y'all should try, right? I will say I'll do this little section of practice here with you, and then you know, you should complete this. There will be an assignment that will go up. If it's not up yet, you can do the questions and then just wait for the assignment to go up. But this reaction has CO2, so carbon dioxide, hydrogen, and heat. This is the left side, so those are my reactants. On the right side are my products. So before we get into the shift, is heat absorbed or released, right? Because heat is on the left with the reactants, that means it's absorbed. Part B is what will happen to the shift. All right, so if my stress is I add carbon monoxide, CO, right? So where is carbon monoxide? Well, it is on the right side. Because I'm adding to the right, I need to go away from the right. So it will shift left. Left is away from right. If I add carbon dioxide, all right, carbon dioxide is on the right side. So again, I'm adding. If I add, oh, sorry, it's on the left side. If I add to the left, it should go away from the left. Well, that means it goes right. Okay. If the temperature is increased, well, this is kind of like code for add heat. Okay. Well, if I'm adding heat, I'm adding to the left side. I need to go away from the left side, which means I need to go right. System is cooled. All right, this is code for take heat. I'm taking away heat. All right, well, heat is on the left. I'm taking it away. I need to go back to the left. So it'll shift left. Right. Y'all should do these examples down here, right? Again, that will be a homework assignment. I'm sure that it will go up. It's probably not up right now in this moment, but it will go up soon. The next little section is solubility, and it's quite a few pages here. I'm not going to do all of this. I'm going to do a bunch of it, but again, I'm not going to do, I'm not going to do every single solitary thing. And that's because I have a little bit of freedom now, because we're not bound by, you know, again, I'm not handcuffed by the regions at this point. That's a little bit good, a little bit bad for y'all, because it means that I can do a little more stuff. It also means that I don't have to do nearly as many things, which is why it's also a little bit good. Anyway. Let's take a look at this. So, solutions. Now, solutions are another thing that we talked about early in the year, and we're kind of doubling back. We're talking about it with new knowledge. A solution is a homogeneous mixture, which means it looks the same throughout. Whatever the substance that gets dissolved is called the solute, and the substance that does the dissolving is called the solvent. So if you have salt water, salt got dissolved, that's the solute. Water did the dissolving, it's called the solvent. If water is the solvent, we say that the solution is, how do I spell aqueous? A-Q-U-E-O-U-S, aqueous. All right. So we talked about that, right? Aqueous is what you call it when you mix something into water. Solutions will not settle on standing, which basically means if you leave it alone for long enough, a solution's not going to, you know, magically separate back into the layers, back into stuff. It's going to stay mixed. It just is, right? Solutions will pass through a filter. So you can't, like, use a filter to separate a solution, right? If you try to filter salt out of salt water by pouring it through a coffee filter, you will be sad, you will have a wet coffee filter, and you will still have salt water. It ain't gonna work. That's not gonna happen, right? Now, there are ways that you can separate solutions. You can do it by evaporation, distillation, And, fancy one, chromatography. Right, you can do a chromatography on pen ink. Right, pen ink is a solution, and you can separate it by chromatography. Evaporation is straightforward. Distillation is fancy boiling. I say it's fancy boiling because distillation relies on solutions that are made of like two liquids that have different boiling points. So when you distill something, you bring it to the boiling point of one of your liquids, but not the other. So you evaporate away one of the liquids and you keep another one. So distilling something is a way of purifying it to a certain degree. Right? There's going to be another lab, which will probably be in the next video, now that I'm thinking about it. Another lab on solubility. It's a bit of a messy lab. I personally am not fond of doing the lab because it's messy. But I also like tend to make people clean up. You know, y'all clean up after it, so I guess I'm not that bothered about it. Anyway, solubility. If a substance can be dissolved into another substance, then we say that they are soluble with each other, right? You talk about like water-soluble paints, water-soluble vitamins, water-soluble stuff. Just means that you can dissolve it in water. Oh, thank you, phone. See, my phone agrees. I was doing really well. I feel like I had that silenced or on vibrate for like quite some time. Anyway. Solubility of two molecular substances depends on exactly one thing. It depends on polarity. Like dissolves like. Polar things will dissolve polar things. Nonpolar things will dissolve nonpolar things. Water will dissolve things that are polar. If something does not dissolve in water, that means that it is not polar. That's it. The ionic substances, I'm really not gonna fuss over the ionic substances bit. However, there is a part of the reference table which I will talk about when I do the lab. So in the next video, when I do the solubilities rules, I'm pretty sure I'll do it. Or if I don't do it the whole lab, I will talk about it like as a case study, about things that are soluble and things that are insoluble. When I talk about that, I will talk more about solubility rules and table F. But right now, I am going to continue moving along here. Right. How you can dissolve stuff, the degree of solubility, right? How much stuff will dissolve into a solvent can also be affected by temperature. Generally speaking, the warmer temperature, a higher temperature, results in more solubility unless it's a gas. As temperature increases, the solubility of gases decreases. And this is why you want to keep soda cold. If soda gets warm, it gets harder for the gas that's in the soda to stay dissolved in the liquid. So as a soft drink gets warmer, the carbonation actually wants to leave even more. Like on top of like hiss, right? You open a soda and you get that hiss because there's some carbonation that leaves. As it gets warmer, the gas has a harder time staying in the water. The water has a harder time trapping the gas inside of it. Additionally, for gases, pressure will affect it. You want to keep that cap closed because you want to keep the pressure sealed, right? If pressure is increased, the solubility of gas in solution increases. And again, this is why you want to keep soda sealed. Ideally, you keep soda sealed and cold, because that increases the solubility of the gas. All right. Now, here is a little section where I said I was going to talk about solutions and that word saturated from before. Most solutions are not infinitely soluble, which basically just means you can't continually dissolve stuff into it. There's a cap on how much you are allowed to dissolve into a thing. When you hit that cap, when a solvent has dissolved everything that it possibly can and nothing else will fit, we say that the solution is saturated. It can fit no more. It's completely filled. Right? Saturated solutions are equilibrium, which we'll talk about again in a moment. The last bullet point in this section will really hammer that home. If we're not to the max yet, surprise, surprise, we say that it is unsaturated. Now, if you max something out and you saturate it, and you try to add more stuff into it, you try to put more solute in, you say, dissolve, darn you, it ain't gonna happen. That solute will just fall to the bottom of the container. If you try to add additional solute to an already saturated solution, then we have a special name for it. We call it supersaturated, which basically is just to say it is more than full. I don't know if you guys can hear that, but the ice cream truck is outside. It's very distracting. I kind of want some ice cream now. I'll get it later. Anyway, saturated is exactly full. Unsaturated is not quite full yet. Supersaturated is like, it's already full. What are you doing? Why are you adding more? Right? The solubility curves on table G. Do I want to talk about? I do. I'm going to talk about the solubility curves. I am not going to talk about parts per million and molarity. I will talk about electrolytes, though. Okay. So I need to add a page of stuff here. I need your reference table. I don't need the whole reference table. I just need table G. Oh, of course, you went away. Come back. Come back. Okay, reference table, table G, insert. Okay, so here is table G, which I'll just move this off to the side, just so it's not totally in the way. All right. Now, table G represents solubility curves at standard pressure. And it says if you're at a certain temperature on the x-axis, and it talks about how much, what's the solubility? How many grams can you fit in 100 grams of water on the y-axis? Now, some of them are really high, like up here, Ki is really high. Some of them are really low. SO2 is very low. Generally speaking, you should notice that most of the lines on this page go up as temperature increases. There are 3 exceptions: HCl, NH3, and SO2. Right? Those, as temperature goes up, their solubility goes down, which means they are gases. Remember, as the temperature increases for a gas, it becomes less soluble. It wants even more to escape the liquid that it's trapped within. Right? Now, how to read this? I'm going to use KNO3. Right? If I have a solution of KNO3 at 50 degrees Celsius, then I can fit up to 85 grams in 100 grams of water. I can fit up to 85 grams. 85 grams would be saturated. I would be completely filled. If I tried to add 80 grams, it would all dissolve. If I tried to add 70 grams, it would all dissolve. 85 grams, it would all dissolve. If I tried to add 86 grams of KNO3, of potassium nitrate, into water, 100 grams of water at standard pressure, 85 grams would dissolve, and I would have 1 gram of, like, crystal stuff. It would just sit there at the bottom. 86 grams would be supersaturated. 85 is completely saturated, it's totally full, all of that will dissolve. The second you try to go over that, it becomes supersaturated. So for each of these compounds, this line represents how much solute, how much of that particular compound will dissolve in water at a specific temperature and be completely saturated. If you try to go above that line, it would be a supersaturated solution. It would be more than full. If you are below the line, you are unsaturated. That means that I could fit more. I'm not fitting any more right now, but theoretically I could, right? I bring this up because down here, right, on a solubility curve, like the ones on table G, the lines indicate the concentration of a saturated solution, the maximum amount that will dissolve at that temperature. If what you have is above the line, it's supersaturated. If what you have is below the line, then it's unsaturated. Right. Now, there are a few of these. Again, really quickly right now, I'd like you guys to try to answer these questions. A, B, C, and D here. I will go over these answers momentarily, but like pause the video, right? Okay, assuming you're back. KNO3, 70 degrees Celsius. All right. So I tell you what, because I can drag this back and forth, I'm going to put it right next to us just so that temporarily I don't have to go too far. KNO3, 70 degrees Celsius. I'm going to go find KNO3. I would say that it's about 134 grams. It's definitely more than 130. It's definitely less than 140. It's a little under halfway through, so I'll say 134. NaCl, so 100 degrees Celsius. I need to find NaCl. That is 40 grams. 90 degrees Celsius, NH4Cl is here. I would say that's about 72 grams. Right. Now, which of these is most soluble at 15? Okay, so 15 degrees Celsius. There's KNO3. And here is NH4Cl. The most soluble is the highest. Oh, that's NaCl. So NaCl, of these three, even though NaCl was the least soluble when we talked about it, it's the most soluble at that low temperature. Right? Now, oh, keep going. No, go. No, go that way. Thank you. All right. Winding down here. Behavior of, again, I'm not going to worry about this math part here. I'm not super intrigued by that. It's more math than chemistry, really. But electrolytes are interesting because they will affect a solvent. Like how you dissolve something in water, how you dissolve something in a solvent will actually affect it. Any substance that produces ions when dissolved in solution is called an electrolyte. Right? So we're kind of expanding our definition of an electrolyte. The ions are free to move in solution, so that solution will conduct electricity. This is why salt water will conduct electricity, but distilled water, literally pure water, not very good at conducting electricity. It will actually evaporate before it conducts electricity. The greater the concentration of ions, if you make more ions, it'll be more conductive, and the reason for that is you have more charges floating around. Electricity is charges moving from one spot to another spot. If you have lots of charges that are able to move, it's very easy to conduct electricity. Aqueous or molten ionic substances, acids and bases, are electrolytes. So salts, acids, and bases. Those are the three things that will qualify as electrolytes, and we'll talk about that a little more. Ooh, I got a Steam notification. That's interesting. Trying to record, not game. Anyway. When you have an ionic substance and it dissolves into water, we have a special name for it. You should be familiar with this name. Just know that it means that an ionic substance is changing into a positive and negative ion. We call it... I think there are two S's in this word. Not that I can spell. Dissociation. Yeah, there's definitely two S's. Dissociation. So they're dissociating with each other. It's the opposite of associating with each other, but they're dissociating. Right, so if you put salt into water, it dissolves because the Na plus ion and the Cl minus ion actually float away from each other. The reason for it is that water, again, water is polar. It has a plus side and a minus side. So the water's plus side looks for the Cl, the water's minus side looks for the Na, and then you just rip them apart. And that's what happens. Now, when you do this, it actually affects some of the properties of the solvent. Right? Generally speaking, the big deal. There's one bullet point with blanks here. If you remember nothing else, adding solute to solvent causes boiling point to increase and freezing point to decrease. It causes them to get more extreme. The boiling point goes up, the freezing point goes down. Right? This is why we put salt on the roads here in Syracuse. The reason for it is because water is supposed to freeze at 32 degrees Fahrenheit, 0 degrees Celsius. When the temperature is right around there, it's very obnoxious because the water on the road can freeze and melt constantly. That's very dangerous. So by putting some kind of salt down on the roads, instead of freezing at 32, now maybe the water on the road doesn't freeze until 28 or 26 or 24. Which means that if the temperature is staying right around 30, even though water is supposed to freeze, the presence of the salt on the road means that water won't freeze until 24 or 26, which means at 30, I still have liquid water on the road, which is generally good, because it's not icy road. It's wet, which is annoying, but not as dangerous as icy roads. This is also why, when we did the cooling curve for Water Lab, I added salt to the snow. It depressed the freezing point, which meant that snow was not at 0 degrees Celsius, it was at like -5 or -6 or -10. Which meant the water inside the test tube would freeze that much faster. Alright? Boiling point will go up. This is why you put salt, one reason that you put salt in water if you want to boil water for pasta. Water is supposed to boil at 212 degrees Fahrenheit, or 100 degrees Celsius. And if you put salt into the water, it dissolves. Instead of boiling at 100, it might boil at 105, or 110, maybe 112. Basically, it means that you have hotter water. If your water is hot, pasta will cook fast. If your water is hotter, pasta will cook faster. So you can get to eating faster, which generally speaking makes people happy. But if you add a solute to a solvent, if you add something to water, it causes the boiling point to go up, it causes the freezing point to go down. They get more extreme. They get further away from each other. Right? The reason for that is more or less, it's easier to explain with freezing, actually. When you freeze something, you put it into really nice, exact, perfect patterns. Well, when you add solute to it, that's more particles, and those particles get in the way of that really nice, perfect pattern. So now the water molecules have to, arrange themselves around these dumb other particles that are just sitting in the way. And because of that, it requires more time, it requires more effort, they have to expend more energy in order to arrange into a pattern. Right? So that's physically what's happening, is that there's stuff in the way of the pattern. Right? Now, I have one last little topic to go through. And it looks like a lot, but there aren't a ton of blanks. And nuclear chemistry is pretty quick in the context of what we're doing. Right? It's pretty quick. Nuclear chemistry is where the rules kind of stop applying. We have had a lot of rules for chemistry. We've had a lot of definitions, a lot of things that have been it has to be this way and it can't be that way because that's what we're saying. Nuclear chemistry is where we start to kind of cheat the rules. We'll bend the rules. And the reason we do that is because we call it nuclear chemistry specifically because these are things, these are changes, and these are reactions that take place inside of atomic nuclei. They happen literally inside the nucleus. Nuclear chemistry means you are changing the nucleus, which up until now I've told you, no, you don't change the nucleus, especially the number of protons. We get to start changing the number of protons. Right? Nuclear reactions and nuclear equations still follow the big rules. They follow conservation of charge, they follow conservation of mass, they follow conservation of energy. Those three still followed. The other rules that we mentioned, where like you're not allowed to change the number of protons, and you don't change the stuff in the nucleus, and they don't react with each other because they're too far inside, we get to bend those ones. In a nuclear reaction, the sum of the atomic numbers on the left and the atomic numbers on the right have to be the same. That's charge, right? This number down here is 92. If I add 90 and 2 together, that's 92. Also, the mass on the left and the mass on the right has to be the same. Well, that's what we said before. Conservation of mass. We used to say that that meant 1 carbon on the left and 1 carbon on the right. Now, in nuclear chemistry, it just means that this number up here has to match these numbers over here. Right? This specific nuclear equation is changing the number of protons. We're changing what we have. Bending the rules. This is uranium breaking down into thorium and helium. So in this nuclear reaction, because the uranium nucleus releases protons, it becomes thorium. It becomes a new element. Because remember, if you change the number of protons, then you change the actual element that you have. Now, the thing with stuff over there, that is called radioactive decay. And it's decay because it's a breakdown. You're breaking down into smaller pieces. This is like a decomposition. It's a fancy decomposition. Nuclei are composed of combinations of protons and neutrons, which you know. And most nuclei, most of the stuff in the periodic table, are very stable. However, all the nuclei greater than... Oh, goodness. This is something that, off the top of my head, I don't always recall. All nuclei greater than 83. I'm about 85% certain of that number. But, oh, goodness. No, don't do that. All of your nuclei with atomic number greater than 83 are considered unstable, and an unstable nucleus has a very special name, very special term. We say that it's radioactive. So radioactive material, radioactive elements, radioactive things are just unstable. Now, that is also not to say that everything under 83 is always perfectly stable, because carbon has radioactive versions. Potassium has radioactive versions. Nitrogen has radioactive versions, right? There are radioactive versions of other elements too. Just so happens that the bigger they are, the more likely they are to be unstable, right? So for any element, which an isotope that is unstable and radioactive is called a radioisotope. Radioactive isotope, radioisotope. We just Frankenstein the words together. Now, all radioisotopes, all unstable things will eventually become stable by decaying. It will decay somehow, right? There are four. There are 4 basic types of radiation. Some of them are more dangerous than others. Right? The 4 types of radiation are alpha radiation. An alpha particle is a helium nucleus, 2 protons, 2 neutrons. So that's one type of radiation. The next type is a beta particle. That's a fancy name for an electron. So beta particles are electrons. If you know your Greek alphabet, you know the next letter is gamma. A gamma ray is a form of pure energy, super dangerous. Alpha particles, beta particles, like meh, whatever. You can get hit with a bajillion of them and you'd be fine. You might feel a little tingle, but it's like, oh, that was annoying. Gamma rays, no bueno. Also, don't turn you into the Hulk, don't turn you into the Fantastic Four. You just, like, are sad. And probably dying. Gamma rays, no good, alright? That's what I'm getting at. And the last kind of radiation is something that you've seen that has always been like a dummy answer. It's always been like, yeah, don't pick this, all right? A positron. A positron is a positive electron. Positron. We start to just combine words to make new words at some point. With 4 types of radiation: alpha, beta, gamma, positron. All right? Which means there are 4 types of decay: alpha, beta, gamma, positron. Alpha decay means the atomic number goes down by 2, the mass number goes down by 4, because we're spitting out an alpha particle, so we're spitting out 2 protons and 2 neutrons. Beta decay is spitting out an electron, so the atomic number is increased by 1, mass stays the same. Positron means we're spitting out a positron, so the charge on the nucleus decreases by 1, which means atomic number decreases by 1, which means number of neutrons increases by 1. That's a weird one. When you emit a positron, you actually go through the process of converting a proton into a neutron. It's kind of completely bizarre. I get into it with the physics class just the tiniest bit because it's this weird thing. Again, all year I've basically been saying that protons, neutrons, electrons, that's the smallest stuff that we know of. It's totally not. There's stuff smaller. If you take the pieces of a proton and you rearrange them properly, you can make a neutron and a positron. It's the same amount of stuff, just rearranged. But again, nuclear chemistry is where we get to bend the rules. And then gamma is gamma ray. Like, boom. Alright. Now, relative strength. If you want to protect yourself from an alpha particle, you could do this. You could take a single piece of paper and just hold it up, and you would be protected from an alpha particle. If you wanted to protect yourself from a beta particle, you'd want to take a piece of cardboard, maybe a bunch of pieces of paper, and just hold them up, and you'd be protected from a beta particle. Or a positron. They're exactly the same except for the charge. So beta particles and positrons, you can protect yourself by just holding up some paper. A lot of people, maybe cardboard. Holding a piece of cardboard. If you wanted to protect yourself from a gamma ray, you would need about 3 to 4 feet, closer to 6 feet of concrete, or 8 to 12 inches of lead. That would protect you from gamma rays. Anything other than that, gamma rays will get through to you. They're very dangerous. No bueno. All right. Now, I'm going to very quickly, very briefly, talk about transmutations and fission and fusion. I'm going to hold off on half-life. Again, math. I'm more interested in a lot of these concepts than I am in the calculations. Because I think the concepts are more of the science. The calculations are a little more math, and I will leave that to your math classes. Now, transmutation is this wacky thing that old school scientists used to refer to as alchemy. Alchemy was this branch of science once upon a time in which people legitimately thought that you could turn anything, you could transmute anything, any common material, into gold. Now, they picked gold because it's shiny and pretty and bright, and we like things that are shiny and pretty and bright. That's why we like gold, that's why we like diamonds, rubies, emeralds, silver. Precious metals are precious to us because they're shiny. That's it. That's the whole reason. That's why they're valuable. Right? We value shiny things. But transmutation is the process by which you take an element and you transform it, you transmute it into a brand new element. Now, all those alchemy guys were wrong. You cannot, in fact, take literally anything and turn it into gold. That's just not how this works. There are some things, some elements that you legitimately can transmute into other elements, and some of them will happen on their own. The spontaneous disintegration of an atomic nucleus. Ooh, lots of cool words there. Spontaneous means it happens on its own. Disintegration means it's breaking apart, and the atomic nucleus. So the breaking apart of an atomic nucleus, if it happens on its own, is called natural transmutation. And during this process, an element may change into another, which is, again, the process of an element changing into another element is called transmutation. I guess you can also call this radioactive decay. That's probably what Ms. Summers and I were going for there. Transmutations can occur naturally or artificially. Again, there are some man-made things that we can transmute. If you have alpha, beta, positron, those are all natural. Those are forms of natural transmutation. If you're looking for natural transmutation, right? If I ever ask you what's natural transmutation, an example of natural transmutation, it's only going to have a single nucleus. It's going to have a single reactant, one reactant. That's natural transmutation. Artificial transmutation, which is what we could do to some elements. Artificial transmutation. Yeah, words. This occurs when you take a nucleus and you just hit it with stuff. You fire stuff at it. Usually alpha particles, maybe neutrons, but you rapid fire these really small particles at a nucleus, which means two reactants. So artificial transmutation means two reactants. There are two big types of artificial transmutation that we actually use, and we use productively. So when we talk about nuclear energy and nuclear power plants, that's an artificial transmutation. We are transforming something into something else. One type of artificial transmutation involves the collision of a charged particle with a target nucleus. And we charge the particles, the charged particles are accelerated. We move them along through these giant machines. We call them cyclotrons and synchrotrons. And what they do is they force them forward because like charges repel. So if I have a positive charge here and I just have a positive charge constantly behind it, I can push it forward. And we do this just exceptionally fast. These things happen exceptionally fast. They're also exceptionally big. There is a cyclotron beneath Cornell University that is a few miles wide. Like it's dug underground. It's a giant like tube-looking thing, but it's enormous. You could walk through it. But maybe it's more than a few miles. It might be 8 miles across, like diameter, right? So we take these charged particles and we just spin them around and we hope that it hits something. Another kind of artificial transmutation happens when a neutron collides with a target nucleus, and neutrons can be created as a byproduct of some kind of nuclear reactors. And again, this is where we talk about nuclear power, right? So we have these two kinds of artificial transmutation. Well, actually, one of them is natural. The other one is a little more unnatural. But we have... Stop buzzing. Stop that. Okay. We have fission and fusion. Fission is splitting things apart. Fusion is forcing things together, right? So a fission reaction involves the splitting of a heavy nucleus to produce lighter nuclei. So if you look, uranium-235, right, has a mass of 235. It splits into 142 and 91. Those are comparatively smaller. Fission reaction takes one really big thing, fires a neutron at it, and makes smaller things. Now, the other thing I want you to notice is I start with one neutron. I need a neutron to do the reaction, but I make 3 more. Those 3 neutrons will go and make 3 more fission reactions, each of which will make 3 fission reactions on its own. So 1 turns into 3, turns into 9, turns into 27, turns into 81 to 240. This is a chain reaction. This is a self-sustaining chain reaction because the products of the original reaction result in more reaction. As long as there is uranium to hit, this reaction will continue to take place. Fission reactions are fairly dangerous because they are chain reactions. They will tend to continue happening as long as you have a heavy nucleus to split. Right? Fusion reactions. A fusion reaction involves the combining of light nuclei to produce something heavier. So again, like, this has a mass of 3, this has a mass of 2. They combine to make something with a mass of 4, like technically heavier. Fusion always involves hydrogen and helium. Fusion is the way that stars produce energy. Our sun uses a fusion reaction. It takes hydrogen, it slams them together, and they make helium. The other thing they make is an enormous amount of energy. Right? Fission and fusion convert a tiny amount of mass into an enormous amount of energy. They're both fairly clean. Right? Fusion and fission are they do produce some radioactive waste, but they're largely clean energy, right? Nuclear energy is way cleaner than coal or oil, any fossil fuels, right? Hydrocarbons. When we get into organic chemistry, we'll explain why that's dirty. But nuclear waste can be more difficult to dispose of, but overall, cleaner process to create a ton more energy than fossil fuels, right? Now, there's a little bit more, but that has to do with half-lives, and I'm not super concerned with those. There will be assignments littered about the week, talking about reaction rate and kinetics, talking about solutions, talking about nuclear chemistry. Keep your eyes open for them, alright? If you have questions, please email me. Otherwise, I will see you about this time next week. Take care, kids.